Hello dear students, welcome back to my YouTube channel. Am I audible and visible to all of you? Please let me know. Am I audible and visible to all of you? So I'm just waiting for your response. Hello all of you. Hello Bida. Okay. So I guess we are having the class after 1 week. No? So so I guess today will be our last class for electrostatic part first, right? So today we are going to discuss about equipotential surfaces and conductors and its properties. So this will be probably the last class. And from second class, so we will be discussing capacitor. Okay, capacitor either or we can be doing electrical current, right? So equipotential surfaces and conductors and its properties. So this will be probably the last class. From okay, so let's start then. So as you know that in my last class we had the discussion on the frequency, right? So if we can see from this particular slide, okay, so it comes to the first slide. It's first slide. This one. Just give me 1 second. 1 second, Betaji. Okay. So these are some things that we had discussed in the last classes, in few last classes. Okay, so this was my last class, no? Electric dipole thing. Dipole was my last class. He put it and the potential. Yeah, this was my last class in this particular slide. So yeah. So in today's class, we will be discussing about equipotential surfaces. Okay. So what basically is equipotential surface? I guess I'm audible now. Aroshi, am I audible fully? You can just let me know now. Am I audible fully? Huh? I shifted to different place now. So that's why it's something different. I can just see the background is different. Yes. Good now. Good to go now. Once again. Okay, so I need to start now. Once again, I'm just placing the phones so that I will get a very good sort of comments also. Look now. So what is basically equipotential surface? As the name suggests, it is equipotential. Equi means same. Equi means same. Potential that we know now, kq by r. Suppose we will take an example now. If we have a here charge, a point charge plus q. Okay. Now, if we go r distance to right side here, r distance. So we know that here, so we will get a potential now V. Okay, get a potential V. And what is V? So Q by R. Okay. If we get same distance R here, so I guess my value will be V also. Okay. If I go Q R distance in left side, this R. Okay. If I go R here, if I go R here, it is V. Okay. Why? Because V is equals to this K Q by R, KQ by R. You can see from this figure, sir, K is constant, so it is constant everywhere. It doesn't change. Q, same charge is everywhere. No, this same charge, this one. Okay, this Q is constant. No? And look now, it depends on the radius or the distance between the point and the charge particle. Look here, from this particular point to this particular point, if let's put is V1, so I can write that K Q by R. This one I can write it as V2, it is K Q by R. It is V3, it would be K Q by R. Same, it is V4, I can write it as a K Q by R. Done. Let's take one more point here now. I will go R here, I will get V5. I guess V5 is also KQ by R. Yes, sir. If I go here, with same distance R, I will get V6, same KQ by R. So if I join all these points, right, I will get a surface. If I join all these points, I will get a surface. So on this surface, at every point, my potential will be KQ by R. Why? Because the distance is same, it would be KQ by R. So this particular surface, we can call it as an equipotential surface. We will call it as an equipotential surface. So why? Because at this surface, every point the potential is same. So these types of surfaces are known as equipotential surfaces. These surfaces are known as equipotential surfaces. Okay, so you can see now the potential of V1 up to the V5 or V6 is all the values are same, so we can call them as a equipotential surfaces. Easy. Okay. So let's take a second example. Okay, so if we have a line charge, infinite line charge, we know it, infinite line charge. Okay, this one, it has charge positive on it. No, if I go r distance here, r distance here, or r distance here, okay, it is surface will look like the cylinder. Its surface will look like the cylinder. That means at equal distance, potential at equal. Here the potential is V. Here potential is V. Here potential is V. Here potential is V. Okay. So this particular surface, the white one, is an equipotential surface. So you can note down two things here. If we have point charge, for point charge, my equipotential surface looks like what? Sphere. Looks like sphere. But if we have a line charge, if I have a line charge, so for line charge, the equipotential surface will be a cylinder, okay, cylindrical, shape. Then very easy. Okay, now let us do some sort of more things about the equipotential surfaces. Okay, I'm not feeling well, that's why I'm speaking slowly. Okay, manage this video. I'm facing a lot of trouble with my health right now, so you need to just manage, right? Okay, let's suppose here we have a lot of things now. Look, if these lines represent electric lines of forces or fields, and these are parallel to each other, right? Someone is explaining me. 1 second. One second, what are you? Okay. Okay, so if we have a uniformly electric field lines now equidistant apart and same direction, just taking some points. If I take a point 1 here, okay, point number A, this one is point B, this one is point C. These are electric field lines. Okay, done. Now we know that this particular line represents electric field, and if I want to go from A to B, I want to go from A to B. What I will write here now? We know one equation now. So what we know? We know dV is equals to minus E dot dr. We know this. dV is equals to E minus dr. Okay. So dV equals to minus E dr. Look, this is my dr displacement across AB, and this is my E. So angle between will be 90 degrees. So can I write here? Can I write here? So it would be okay, is cos theta theta. You can write here dV is equals to minus E dr cos 90, and we all know that cos 90 is 0, so dV came out with 0. So dV means potential at final minus potential at initial close to 0. So I can write VB is close to V. Do you know what is the reason of it? Why potentials are same? Why VB is equal to VA? Okay, because these are the same distance. At same distance, potential is every time same. That's why you will call it as an equipotential surface. So if I need to make an equipotential surface for uniformly electric field, look, if these are uniformly electric field lines, okay, and I need to make a this equipotential surface, how I need to make it? Look, it will looks like this. Okay. This sheet represents what? Equipotential surface. It is what? Equipotential. You need to imagine it now. Equipotential surface. You need to imagine it. This is very easy. Okay, it is equipotential surface. And I just prove it also know why it is equipotential surfaces. So if lines are going in this way now, look, one line, second line, look, and my equipotential surface will be perpendicular to it. Okay, easy. Let's do one more numerical, and this numerical was asked in NEET. Okay, let's do a NEET PYQ. Let us do a NEET PYQ. So we have electric field lines going in this way. We have electric field lines going in this way. Right? Here is my point A. This is point B and point C. So we have to mark potential difference between them. If I can write VA is more than VB, more than VC, first. Second one, VC more than VB, more than VA. Third one, VA more than VC, more than VB. And fourth one, VB more than VA, more than VC. Okay, how to solve it? To get this numerical done, we need to remember one property, that is, if we are going along the electric field, if we are going along the electric field, potential decreases. So I will write here along electric field, potential decreases. Potential decreases. If you remember this line, so the answer for my question is this one. Okay, so my VB is more than VA is more than VB and VB is more than VC. We can like this. Okay, done. Okay, now one more point, and the one more point is like that. If we want to take a particle, okay, if we have particle and if we want to take a particle from one point to different point in this equipotential surface, if we have particle, okay, if we have a particle and we want to move this particle from one particular point to second particular point, but both those pointers are at this equipotential, simply indicates. Look now. So look. So work done by external field or the electric field in taking a particle from one point to different point, we know a simple formula, that is W equals to V final potential minus initial potential. If we are dealing with equipotential surfaces, so Vi equals to V final equals to V. Why? Because we are dealing with equipotential surface. We are dealing with equipotential surface. Look better. Suppose this figure we have now, r distance. Particle is here. I want to take this particle from this particular position to this particular position. Huh? You can look now here, potential V initial. Is it KQ by R? Perfect. It is. This one is final, V final. Is it KQ by R? Yes. I can write V initial equals to V final equals to V. It is what? Equipotential surface. Right? So what I can write here now? I can write here. So work done by external force is equals to Q to V minus V. So work done by external force to take a particle in an equipotential surface will be how much? 0. So work done by external force or work done by electric force. Work done by electric force to take a particle from one particular position to different one, but both should be inside an equipotential surfaces. So work done will be 0. Okay. So look now, one more thing that we can derive from it now, and that would be like, look, what is dV? So dV is equals to minus E dot dr. We know this one now. So in equipotential surface, dV is 0. I can write dV is 0 equals to minus E dot dr. Or I can write it is E dr cos theta equals to 0. Look, from this particular figure, E can't be 0 now. E will not be equals to 0. Electric field will be present. Displacement will not be 0. Okay. So therefore, only cos theta would be 0. So at what particular value my cos theta is 0? So theta is 90 degree. Okay. So this particular point indicates that in equipotential surfaces, angle between R and electric field is 90 degree, or you can write electric field is perpendicular to R. Electric field is perpendicular to R. This particular thing you have to remember. Electric field will be perpendicular to R. Done? Any issue? It's very easy now. I don't think you have any kind of issue. You should have any kind of issue with it now. So I will give you 1 minute. If you have any issue, you can just ask me here. Okay, I will wait for your comments. Then we will just move ahead. Okay, I guess you don't have any kind of issues with this particular topic. So we conclude the equipotential surface as well. So let us go to the different one, and the different one is conductors. Okay, conductors. As we know that from the previous some lectures, what conductors are. So conductors means these are those materials which have abundance of free charge particles. Okay, very free charge particles. Okay, so if we have a conducting sphere, what this figure represents is it's a conducting sphere. The conducting sphere. So as you have taken a class of first one, in first class we had discussed about behavior of conductors and non-conductors. So conductors charge will reside on the outer surface only. Okay, here the figure is symmetrical, so it will be uniformly, and inside will be zero. Okay, because inside there is no presence of charged particles. So with the no presence of charged particles, my electric field will also be equals to zero. Okay, let's suppose we have a we have a asymmetrical any partner. Let's suppose this much, this shape. So if we have this shape, how charge distribution will take place? It will be non-uniform. We know that inside also in there now it will be zero, but charge distribution will be non-uniform. It will be non-uniform. Okay, and one thing that you need to remember now, that is charge density is inversely proportional to the radius of curvature. Charge density is inversely proportional to the radius of curvature. What does it mean? Look, if we take this one now, look, this one, this point, look, make a circle of it now. This point, make a circle out of it. This point, make a circle out of it. Okay, so I guess this one is smallest now. If this is smallest, so my maximum charge will be here, maximum charge. Okay, here charge will be somehow like this, no? To be like this. Okay, so that means if we have a very sharp edge on particular sharp edge, my charge will be maximum. Okay, so you need to remember this particular equation. This equation you need to remember. Charge density is inversely proportional to the radius of curvature. Radius of curvature. More radius of curvature, less charge density. Less radius of curvature, more density. More dense particles will be there. Okay. On this particular phenomena, your Venn diagram generator is there, na? Which is not present in your syllabus, na? But it is present in South Indian textbooks. Yeah. So if we have any shaped sort of conductor, any shaped sort of conductor, okay. If we have any shaped conductor, look now, this one, okay. Look, 1 second. So look now. So this one is my any conductor, any shape. This much, okay. So we know that E inside will be zero. E inside is zero. So my particle will be like this, okay, something like this. Okay. So I will take this area. If the area is D, small area, I will use Gauss's law. Okay, only this particular area I will use a Gauss's law, Gaussian surface. Look here. So the area of this particular portion will be also dA. So electric field will be outwards. This is my electric field. Okay. So what is Gauss's law now, sir? It is E dot dA equals to charge enclosed by epsilon naught. Done. So look now, area vector will be outwards. E is outwards. So can I write E dA cos 0 degree? Yes. Charge enclosed by epsilon naught. Cos 0 is 1. I can write E dA on. It is EdA. What is charge now? If the charge of hole is Q, so the charge of this one would be how much? dq. Okay, what is charge density? Sir, charge density would be charge by area. I can write dq equals to sigma dA. So here I can write sigma dA by epsilon naught. I can write like this now. dA cancel out, so electric field will be equals to sigma by epsilon naught. So electric field outside of any conductor is equal to sigma by epsilon naught, and this is the derivation that I just done here, right? It is just outside, right? Just outside the conductor, just outside the conductor. Okay, inside is always zero, no? This is how you need to manipulate, and you will get your answers. Okay, very simple. It's very simple. So the next topic that we need to discuss now, that is electrostatic pressure. Okay, a good sort of topic. A lot of numericals were been asked from this one for your aims, so that's why this is important now. So let us suppose, okay, I will just write for you the electrostatic pressure is electrostatic pressure. It's electrostatic pressure. Okay, okay. So this is not some random shape part, some random shape conductor. Okay, okay. What I can do now, I will just divide the particle. Let's say I will take one element, this one, and the whole. So can I write it like this? One like this plus one like this. And if charge is Q on it now, so here I will write Q. Okay. So here charge is something like that. Okay. Look now. Due to this one, E inside is zero. We know the E inside is zero. E inside is zero. Okay. Okay. Due to this particular portion, electric field is E1. It will be outside. It will be E1. Okay. Due to this rest thing, okay, my electric field will be in this way, E2 and E2. Okay, but one thing that we need to know now, that is inside it is zero. If inside it is zero, can I write now E1 plus E2 will be equal to zero? I write like this. They need to cancel it out now. Okay, so it is not E1 plus E2, it is E1 minus E2. Okay, because direction is different, so I can write E1 equals to E2, both equals to E. Then due to this one, electric field will be E1 here, electric field will be E1 here. Due to this one, electric field will be E2 here, and here it is E2 here. Okay, so look now, if we just add these two now, so it will be 0, and this condition satisfies. Done. So look now, look now, look now, look now. Outside, this one, outside. What is E? Sir, E is sigma by epsilon naught. But here, E is equals to E1 plus E2 equals to sigma by epsilon naught. Can I write from this one? I can write E1 plus E1 because both are same now. Sigma by epsilon naught. E1 plus E1 is 2E1. So 2E1 equals to sigma by epsilon naught. So I can get E1 sigma by 2 epsilon naught. Then look now, look now, look now. What is force? It's force. Is it Q into charge into electric field? Is charge into electric field now? But here we have small elements, so I will write a small charge. I will write a dq charge. I will write a dq charge only now, small charge dq into electric field E2. Force. What is charge? Charge density into area. Sigma by 2 epsilon naught. What is pressure? Force per unit area. What is force? Sigma dA sigma divided by 2 epsilon naught whole divided by dA. dA cancel out. It is sigma square divided by 2 epsilon naught. this one. So if you need to get your electrostatic pressure, so the electrostatic pressure will be equal to sigma square divided by 2 epsilon naught. Sigma square divided by 2 epsilon naught. Okay, sigma square divided by 2 epsilon naught. It's my electrostatic pressure. What do you need to do now, beta? You need to maintain a separate formula sheet. No? I guess in my Telegram group I also shared a one mind map. No? Okay, I'll see what you can do now. With the lecture series, you need to know down only these points. Electrostatic pressure is sigma square 2 epsilon naught, like these things. No? Right? Because when you are doing your numericals, no, you don't need to do the whole derivational part. You have to remember the formula only and do the numericals. Done? Okay, look now. One more thing. If we have any sort of conductor like this, okay, conductor, we know if it is conductor, so E inside is 0. This point number 1, point number 2. We are taking a particle from 1 to 2, like this. Find the potential at 1 and 2. We know that. Sir, dV equals to minus E dot dr integrated from V1 to V2 or 1 to 2. Okay. Inside, what is inside? Sir, inside is 0. Can I write it V2 V1 equals to 0? Yes, sir. It is V2 minus V1 equals to 0. Yes. So V1 equals to V2. So potential at this one and potential at this two is same, but E is 0. So you will get a question. If my electric field is 0, so is it compulsory that my potential needs to be 0? So you will get a question now, beta. If E is 0, potential is 0. Is it compulsory? It may be now. It may be. It is not compulsory. If E is 0, V is 0. Okay. You can do one thing, sir. Sometimes my V is 0, E is not equal to 0. Dipole case, no? You can take it. Okay, so here you can write, sir, here E is 0 but V is constant. Then these are some things that we will get from it. No? So I know that this question will not come to examination, but what will come now? This parameter. So if E is 0, V should be 0, or V V must be 0, or V needs to be 0. This is how we can do it. So if I need to make a graph of it, now look, R V. So in this conductor inside, my potential is what? Constant. Now it will be constant. Then it is Q by R. Okay, 1 by R. This is constant. What is Q by R? Constant. This is constant. Up to this what? Up to the surface. Okay, let us do some 2-3 points. Then we complete the chapter. Okay. So one more thing is my electric lines of forces are perpendicular to surface. So if we have any surface, any surface, okay, and if you need to draw an electric field lines, those lines will be at 90 degrees. Okay, every time. Do you know why? What's the reason behind it? Suppose if it is not 90 degree, na? Suppose if it is not 90 degree, what will happen then? Hmm? I will tell you now. Look, we know one thing now. Look, this surface is equipotential. We know it. It is equipotential. We know it. Why? Because inside it, V same. It is KQ by R. We know it very well. One second. Okay. So let us suppose what we can do now. So if we take any surface like this, and on the surface, if my electric field lines makes some angle, no? Some theta angle, I need to just draw it in this way. Look, one component will be along the surface. Along the surface. One component will be along the surface. If there is an electric field, okay. So this electric field, if we had this electric field now, look, if we zoom it now, this is my surface and my electric field in this way. So if we are a charge particle will move on the surface and electricity will get generated. Electricity will get generated, which is not possible. Which is not possible now. Or one more reason for it now. Look, if it is an equipotential surface, right? So my E needs to be 0 on the surface. No? Look, E is 0. Then if E is present, if E is not equals to 0, so how you will write that dV is equals to 0? So it is not possible. So here you will write so equivalent surface, so dV equals to 0. If dV needs to be 0, so E needs to be 0. That's why. Okay. So one question that was asked in, I guess, in NEET or in IIT, and the question was like this. No? We have a sphere like this. One line is like this. One line is like this. Center and just like this. Okay. Which one is the character representation? 1, 2, 3. 3. Why? Because inside this conductor line won't be possible. Look, this line is not making 90 degree. This is making 90 degree now. So you can write, yes sir, this one is correct. Third option is correct. Third option is correct. Okay, now we have the last problem, is cavity problems. We have last one, that is cavity problems. Look, if we have a conductor, okay, and we cut a here, this is our cavity. Okay, now inside a cavity we place a charge particle minus q. Due to induction, here my charge will be plus q, and here my charge will be minus due to induction. Or one more thing, if it is like something like that, here I have charge particle. Okay, it's solid now. Here I have plus q charge. It here I will get a minus q. Here I will get a plus q by induction. These are induction parts. Induction now. I know that. I guess you know now. Look, induction doesn't create any charge. Now, induction is only that redistribution of charge. If we know, look here. Sir, the charge on this inner surface is minus q, outer will be plus q. What is the whole? Sir, whole will be 0. Yeah, initially the charge was 0, finally the charge is 0. Only what happens is that redistribution happens. These charge particles get created due to the induction part, due to the induction. Okay, I hope this lecture was good. My health is not permitting me now to just be a loud now, be a very energetic. My health condition is not that good. So probably next time I will be having a very good energy for the class. So this from this topic we completed our lecture. Okay, and we completed this lecture also. We completed also our chapter completed. So we completed our whole chapter. Okay, if you have any doubts or anything like that, you can just go to my Telegram. Okay, there you will just send me a message also. So how you will get Telegram? You will get to channel description part. Channel details you will put, and you will find my Telegram link there. You will just open Telegram and you will get my things, right? So I guess for today it is more than enough, and we just complete this thing. And next time we'll be starting the new lecture. And you also know that we are trying to complete the syllabus as soon as possible, because then we will start our 11th standard also for NEET students and JEE students now. So before the examinations to start, we need to just complete whole syllabus. That means up to the Jan or Feb of 2026, we will complete whole 12th and 11th as well. So don't worry about anything. And in the class, I will be sharing something great now. Join the Telegram as well. So for today, it's more than enough. So bye, beta. Bye. Good night. Bye.